Hi, Karpagam. Maybe let's get started in like 5 minutes. Maybe like let's wait for a few more people to join the session. If no one else joins, like we'll still start in 5 minutes. Okay, so maybe since a few of you have joined the session, I guess we can get started. So maybe just to reintroduce myself. So hello everyone, I'm Lakshya Saggi, the problem solving TA for the Monday 6 to 8 p.m. sessions for NPTEL Social Network Analysis course. I believe this will be our sixth session, and in this week we'll be uh, discussing more about. So last week we ended the discussions on like what community detection methods only, where we discussed in the last what is modularity. So we'll continue from there. We'll discuss some further methods of like modularity, permanence, and overlapping community detection. So all of these have been covered in the lectures, but maybe we'll just be going through we'll be just doing a quick revision of everything, and then at the end we'll have some problems which we'll be discussing, like always. So yeah, I guess we can get started. I'll maybe just share my screen. And also, like if there are any doubts or if my voice is unclear or my screen is not visible at any time during the session, please feel free to inform me via chat. Help you as I'll try to help you with them to the best of my capability. And Karpagam, so you had few doubts in the assignment 5. Okay, maybe like we can take those doubts also, Karpagam. If we have time at the end, we'll also be uh, doing those doubts about the assignment 5. But for now, maybe at the start, let's just get started with this week's session for assignment 6, and then at the end only we'll discuss the assignment 5 doubts. So maybe I'll just share my screen and yeah, we can start it. So, yeah, I hope my screen is visible to everyone. So yeah, if it is not, like, feel free to inform me via chat. Uh, so this week again, so a large part of uh, the social network analysis course has been dedicated to this community detection module because it indeed is one of the most important aspects of social network analysis. And uh, in this week, like, we'll be continuing from where we left off last time, which was like a community detection using modularity. So note that last time what we discussed was what is the modularity measure, like, but here we did not discuss about community finding. We only discussed about detection. We only discussed it about how to assign scores to some community. So if some oracle of if some person gives you some a community structure inside the network, and you have to assess the quality of the community, like how good is that community which the oracle has given to us, then modularity is a good measure for doing so. Because what modularity measures, so just as a reminder, intuitively what modularity measures is how much does the given community structure differ from uh, the structure when the input graph would be a random graph. Because in random graphs, you would naturally expect that there are no communities which are formed. And since now we have an arbitrary specific graph, then in this network graph, maybe we indeed have some kind of a community structure. To assess the quality of the community structure, you can just say like how much does the community structure deviate from maybe a random network. So yeah, so this was what we discussed previously. So just as a reminder, so one of the formulations for uh, assessing the value of like modularity for a community structure is just maybe if we have some community structure given to us, then we just take sum over like all the communities, the value of this term, uh, which just denotes and this term is also like what is to compute. This mn by e is just the number of edges inside the community n divided by the total number of edges minus kn by 2 times e whole square, where kn is just the degree of the vertices inside the uh, community and something like that. So yeah, so this is what we discussed previously, and now we'll be continuing from here onwards. So this q, like this value q, this is how this is like the value of modularity for a given community structure. Like if someone gives you the community, then how good is the community? The greater the value of q, the better is the community structure. But how do you even find one such structure which uh, actually gives you a good Q value? For that, you will need some algorithms which find these community structures for you. Note that you will want to have these algorithms as polynomial time algorithms, because exponential time algorithms are usually something which we want to avoid, right? Because they are not efficient. So uh, in general, like this community detection problem is like, as we said, is very arbitrary problem. Like how do you even define communities and all? But note that if you're given like, let's say, this modularity, and then you have to say like, okay, give me a community structure in the graph which maximizes this modularity which maximizes this modularity measure. So note that maximizing the modularity measure is again a hard problem. So what we'll do is we'll not maybe have an algorithm which actually maximizes the modularity, but maybe we'll have some heuristics, okay, which maybe intuitively give us a good modularity value. We can't guarantee that the value given to us will be the maximum possible value, but still, like, it would be good enough for us to work with. And one such method is like for community detection, it is modularity maximization. So intuitively, what the so you want to do modularity maximization, but how do you even do this modularity maximization? And for this, there are two common methods uh, which were discussed in the lectures also. So one is the greedy algorithm, and then the second is low end method. And we'll just be going through both of them again. Uh, so yeah, but these are like if you know the modularity measure, then these are just quite intuitive ideas. So nothing too fancy here, but still like these are important because especially Lowen's algorithm is used quite a bit in like detecting communities in real systems. So yeah, these are quite important. So again, like as you may have guessed, like what would be a good greedy algorithm for community detection? It's just okay, maybe uh, like at every step, let's just try to improve the modularity measure. Like let's just try to increment the community structure one by one, so that at every step modularity measure increases by some delta with positive value. So essentially, like it's kind of a local search algorithm where what this greedy algorithm says is that okay, so initially we have every vertex as a different community. Every vertex of the graph lies in a different community, and now we'll try to merge vertices into same communities. And so maybe at first step, maybe let's just look at the vertex one and see any arbitrary neighbor of that vertex. So let's take vertex two and see like if we've joined both of like suppose if these two like so we are looking at only neighbors of vertex one. So suppose we consider neighbor two, then let's just see okay. So there will be some modularity value for this community assignment, which is like every vertex is in different community. But now let's just suppose maybe we uh, take these two vertices, like these one and two vertices together as one community. So now the community structure will be one and two will lies in one community, and all the other communities are singleton vertices. So you'll see like now we'll see here like whether the modularity value is better than what it was in the initial graph. If it is not, maybe like we ignore this and we try the next neighbor. Similarly, we try the next neighbor and so on. So mm, what we do here is uh, we try to see like in what community assignment for this vertex one, the increase in the modularity measure is the maximum. Like out of all these possible scenarios where we can merge this vertex one with several possible neighbors of one, uh, merging what neighbor with this results in the maximum possible modularity increase. Suppose the maximum possible modularity increase in this step. So these three arrows represent maybe like the modularity increase here is three times as much as here. So here the modularity increase is the maximum. And then you consider this as your initial community structure. And now like suppose you can think of this as one and two as the super node. And now from the super node, you have like all those outgoing edges, and from all the singleton nodes also you have some outgoing edges. And now in this upgraded graph, you again do a like you again try to find some edge so that the resulting community has like the maximum modularity value. And this goes on like you try to do this greedy algorithm and this kind of a local search, and you try to keep on increasing it till you can't increase your modularity value anymore. And as you may have guessed already, or you may be familiar, so this is kind of a local search algorithm. And note that it's not really necessary that, so what this algorithm will obtain is a local optima. But note that local optima is not necessarily equal to global optima, but still like it's better than nothing. So that's why like these kinds of algorithms, like because detecting the global optimum in like like according to these measures, which are modularity measure or something, is kind of a tricky task. So usually we'll have to work with heuristics only. And this kind of heuristic works well in real world. So yeah, this works good for us. But even an even better algorithm, which is usually used, is Lowen's method for community detection. And this is a pretty nice extension of this greedy idea only. So in this greedy algorithm, what we initially said was, okay, uh, maybe we have a like uh, after merging all the vertices and everything, maybe we arrive at some kind of a community structure. So here, like suppose you are given some input graph, and then like suppose you're given this input graph, and what actually happened was after doing some kinds of like greedy local search and everything, you arrived at some local optimum. And suppose this was the community assignment in the local optimum. And now what we were previously saying was okay, like the greedy algorithm is stopping because it cannot increase the value of modularity measure anymore. But suppose we want to somehow somehow we want to see whether it can increase even further or it cannot. Then what Lowen method is just saying is okay. Then it says maybe the best way to go about it is think of all of these vertices lying in a single community as a super vertex. So we were considering this as a super vertex in the local search algorithm also. But note that we were not considering these edges, which lie between the super vertices. So in local search algorithm, what we were doing was we were progressively trying to build up these values of community, like build up these values, increase these modularity values using like one edge at a time and building these communities. But nowhere in this algorithm we considered the edges which lie between the community vertices only. So suppose like after adding 1 to 2 and then this, suppose let's say this 1 to 3 edge gets added, then suppose if there was some like 2 to 3 edge present here, we did not consider that edge anywhere. Like we just assumed this as a super node and then we just went about our business. And maybe like, so what Lowen method says is maybe these edges are also useful for us, which lie between the vertices. And so what it essentially says is, okay, like first let's just do the local search and let's just obtain some kind of a optima. And then maybe if we merge these super vertices and let's just take into account the edges which lie between two vertices which lie in the same community. So these intra-community edges are also taken into account. And then we can build up this kind of a condensed super graph of the initial graph. And then maybe again, what we can do is, so this is a new graph given to us and it has some Q value, it has some modularity value. Uh, like this is a community structure given to us and it will have some modularity value. And suppose we try to see whether this can be increased further, then in this graph, maybe the modularity value can be increased. So we see if the modularity value can further be increased. So essentially like the previous local search algorithm only stopped at this step. But now what we are doing is we are trying to increase the value of modularity even further. So what we do is we think of this as super graph and then just run the local search algorithm again. And again, like now what can happen is maybe the modularity measure can increase even further. And you can continue doing this. Like, okay, so maybe you obtain this graph and again you try to do a local search on this graph to obtain the maximum modularity value. So like note that Lorenz method just does not have two passes. It has two passes in this example, but in an arbitrary example, it can be like much more than two passes, like n passes, n plus one passes. Like you can put a limit on like how much passes do you want, but what it can actually do is like, so what Tobin's method essentially does is uh, takes as a graph as input, find the community structure using local search, then build a super graph out of it. Again, find the local again using local search, increase the modularity value. Then again, you obtain a condensed super graph. Then again, do a local search on it. Again, you obtain a new super graph, and you keep doing this till you can't increase the value of modularity any further. So, like Loven method is again like it's not a very technical thing. It's again a kind of a heuristic only. So it also like kind of detects local maxima, local optima, but it just tries to extend beyond the trivial local search. It's also doing a local maxima only, but maybe a better local maxima than some other local maxima. So yeah, just that. So nothing too fancy here, but yeah, still like something which is used quite a bit. So yeah, but yeah, after going through this, maybe that was this was like, um, okay, so why are we even considering this modularity measure as a good measure? So we saw that maybe modularity measure works as a good metric in some examples, but there are some limitations to this modularity measure. And note that these limitations are not about the specific algorithms which we are using. Like it's not about the limitation of the local search or the Lovan's method, because these methods are not like actually trying to find community structure. They are just trying to find communities which maximize the modularity. And then we are saying good modularity means good community structure. So essentially, what we are trying to discuss now is the limitations behind this theoretical idea of maybe how good a community attributing how good a community structure is to the value of modularity. And this is where, and these are like kinds of limitations when we are dealing with only modularity. So, one limitation for modularity is the resolution limit. And what is this resolution limit? So it's usually observed when you try to do modularity that well-connected smaller subgraphs tend to get merged with larger communities, even if the resultant communities are not that dense. So if you go through the lecture video, so there was an example discussed here, which was like a ring of cliques. So if there is a ring of cliques present in the, and you have to find the community structure in the graph. So the ideal community structure should be all the cliques should be single communities. But this modularity measure will try to merge some of these cliques together, and maybe that's not the best thing to do for us. So yeah, so that's why like there are some flaws in the inherent idea of modularity maximization. So essentially, like it fails to detect those communities which are well separated with densely connected intra-community nodes, but only a single inter-community edge. So yeah, and then another uh, limitation, maybe like not a very big limitation, but just something is like uh, maybe there can be an exponential number of community structures with same modularity value. So note that there can be multiple community structures which have the same modularity value, and then how do you choose between those structures, which is the better structure for you? So yeah, some might be better than others in some aspect or some regard. Some might be worse off, but how do you choose between them? So this kind of a limitation will almost certainly arise in like all the measures of community detection where it involves like assigning some kind of a specific value to certain community structures, because different structures can lead to same values, and then because it's not necessarily a one-one mapping. And yeah, so this is not that big of a limitation, but this resolution limit is a big limitation in modularity maximization. And so it motivates us, okay, even though modularity serves us pretty well, like it's observed in real networks that modularity serves us pretty well, but it also fails in some cases. So how do we fix even those cases? So so to fix this, maybe another measure was tried and introduced, which is like the measure permanence. So moving up, we are trying to move away from modularity and go towards this permanence. Okay, so maybe yeah, one more thing here. So while maximizing while finding the value of modularity for a network, what you have to do is you have to know the entire community structure of the graph. So for finding modularity of the network, it's not just sufficient to know information about a single or two vertices, or one vertex or two vertices. You have to know like the entire community structure of the graph. So modularity is somewhat of a more global metric. And maybe we'll since like in real world graphs, what happens is, okay, like there are some kinds of online settings where like vertices arrive over time. So suppose there was some initial graph G1 and you had some kind of a modularity value for that graph G1, then let's say another V comes into the graph, and suddenly the modularity value and everything completely changes. And this is probably something which we don't want. Like we don't want to recompute from scratch as soon as a new vertex arrives in a graph. So, so these online updates and this resolution limits are the main limitations of this modularity maximization. So to tackle these, obviously there is no ideal way to tackle every issue, but a way to like handle some of the issues is this permanence. So as discussed, like modularity is a network-centric global metric. It considers the entire network using maximization. So what's the use of this one? What's the one limitation that this permanence metric overcomes is that uh, it is a local metric. So what this means is for calculating permanence of like maybe a community structure, you don't need to have the you don't need to recompute the value of entire community structure from scratch. Maybe you'll just have to look at some local neighborhood and you can update the permanence easily. Yeah. So how do we define this permanence, and and this permanence also overcomes somewhat overcomes the resolution limit. So this permanence maximization works in the example of a ring of cliques example, whereas modularity doesn't. So maybe let's just define what this permanence is. So far we just discussed what are the advantages of permanence over modularity, but maybe let's just define what a permanence even is. So two communities A and B are, so first we say that two communities A and B are neighboring communities. If there exist two vertices between these two communities, so let's say there are two communities A and B, then suppose there exists one vertex U in community A and one vertex V in community B, and there is an edge between U and B, then you will say that the communities are neighboring communities. So yeah. So essentially, then what permanence tries to do is it tries to take into account some heuristics. It tries to take into account the intuition of how do even these communities tend to form in a real world network. So how do these communities usually tend to form? So one measure is maybe for any vertex to be inside one community and not be inside another community. Uh, what it has to do is maybe that vertex should have more connections to uh, the vertices which are lying uh, in the same community as that vertex. So what this total internal connections basically says is that for any vertex V, the total number of edges which lie inside the vertex V's community should be greater than the maximum number of edges to any of the external communities, which is a pretty easy heuristic to think about. Like, okay, if you're lying in one of the communities, you would probably say that uh, one of the reasons you are staying in this community is because you have more things in common with more people in this community than maybe things in common with people from other communities. That's how communities tend to form, right? People with similar interests tend to come together. So one thing is this heuristic one actually takes into account the internal connection, whereas the measures modularity, conductance, cut ratio, which we defined previously, were taking into account total external connection. So maybe in the cut ratio, the volume cut ratio, where we took the ratio between the number of edges present between the cut divided by number of degrees, the sum of degrees inside each of the cuts. That takes into account internal connections. But the other cut ratio example, where we just defined the cut ratio as number of edges across the cuts divided by the size of the individual communities, that definitely does not take into account these internal connections. So yeah, so these internal connections actually, so one good insight is that these internal connections are actually also important in community structures. You just don't need to look at the external connection. And building onto this heuristic, so maybe another heuristic which one can think of, which is important for people to stay in the community in which they are already present, is how strong is the bonding between the people inside that community. Suppose you are part of a community in which uh, people don't have good enough bonding between each other, even though you have more things in common with that set of people, but those people are not maybe that good of friends with each other. Then you will probably sway away from that group and join some other group where even though you have less in common with some other group, but that group is more tightly knit. So then you will maybe feel much better about joining that group and it will give you more friendly feel. Yeah. So this is the second heuristic which they capture for in this permanence metric, which says that internal neighbors should be highly connected. For a vertex V to be lying in a community C, then the internal neighbors of V inside the community C, there should be a high clustering coefficient among the internal neighbors. And as we have discussed previously, also multiple times in previous sessions, that high clustering coefficient essentially means that yeah, the vertices are more tightly connected. Or yeah, and this kind of heuristic is also not captured in modularity, conductance, or cut ratio. So essentially, one thing which permanence does, what is different from maybe other heuristics or metrics, is that it weighs the internal connections much more than external connections. Like Okay, it weighs some external connections also we'll see in the formula, but it thinks that internal connections are very important in forming community structures. So yeah. And then as you have seen, so maybe like yeah, higher the number of internal connections, the better should be this permanence value. And higher is the clustering coefficient among internal neighbors, the higher should be this permanence value. So it should be directly proportional to both of these things. Yeah. So hypothesis one is number of internal connections should be greater. Hypothesis two is all the vertices should be highly connected. And then thinking of this as a formula, like probably a very simple way to think about this is okay, like so let's say the if expression permanence is just equal to like some kind of an evaluation of the hypothesis one plus some kind of evaluation of the hypothesis two. And how do you like so these hypotheses are like uh, so you need some numerical formulations for these, right? And this is how you get these numerical formulations. So note that this first term is just IV divided by E max V, which is like a number of internal neighbors of V within its own community. So number of internal neighbors divided by maximum number of connections to any external community. And just as a normalizing coefficient, you have to divide by degree of V. So this one term captures this hypothesis one. And the second term, which is like 1 minus clustering coefficient of V for the vertices in the same community. So 1 minus Cn of V. So note that the more the clustering coefficient, the lesser is this value, and then the higher is the permanence. So this this term captures this hypothesis too. And then you just maybe some of these terms to capture the value of permanence. So again, like you might think, okay, why are we weighing these sums equally? Why are we taking like a sum as it is? Why are we not taking a weighted sum or something? So that all of these are just metrics, like heuristics, and this is how like, and if you like it somehow if you try to define the heuristic in this kind of a manner, it gives good values for us. So you can't really prove these, but you will have to have like a good experimental evaluations. You can prove some of these things to some extent, but more or less a lot of this relies on experimental evaluations. So yeah. So I hope the value of how do you find out permanence is clear to everyone. If there are any doubts, feel free to ask me in chat. So now, yeah. So now again, like first we define some measure modularity, then we define like how what are the algorithms which maybe finds us good community structures which maximize modularity. Similarly, here we'll want to like so we have defined this measure uh, permanence, and now what we'll want is to have some kind of algorithms which maximize this permanence. Yeah. Okay. Maybe just maybe one small last thing that how what do we say is the value of permanence for the entire network is just summation of permanences for all the vertices we individually. So yeah. So as you can see, like so if like suppose there was a graph G which was given to you, and then some new vertex V gets added to it, then like you just need to calculate the permanence for this new vertex V, because the sum will remain the same for the previous vertices. So then to final permanence for the network, you don't need permanence for all the vertices of a local metric, because you can compute permanence for each V individually, whereas this kind of notion did not exist in modularity. Like there are like extensions of modularity which handle this also, which is like localized modularity and stuff, which also has been covered in this week's lectures, but I'm kind of skipping that. But this kind of a thing can be taken care of. Like so in modularity, we said that it's a global metric, but there are notions like local modularity, which also handle this kind of thing. But yeah, like let's not get into that, and let's just stay on this permanence. And note that you can always prove that permanence value will range between -1 and 1. Essentially, what we'll need to show is that this expression will always lie between -1 and 1. And it's like really not too hard to prove. Like so, let's just maybe see what's the maximum value that this expression can take. The maximum value that this expression can take is maybe when I of V is maybe like the degree of V. Like v's like all the vertices of v, like all the neighbors of v lie in the same community as v. So this becomes degree of v divided by Emax of v. So Emax is the connections of v to an external community. So maybe it's just zero, but we don't take zero, like we just maybe add one so that we don't have a division by zero problem. So this thing just becomes degree of v divided by one times one by degree of v. So this term just becomes one. And then you have like minus of one minus clustering coefficient of v. And clustering coefficient is the maximum value of clustering coefficient is always like one. So if clustering coefficient is one, then this one minus one becomes zero. And so this whole thing becomes just equal to one because of contribution of this thing. And this thing becomes zero. So like at least this shows that yeah, permanence, maximum value of permanence for a vertex is always one. Similarly, you can show that minimum value is always minus one. Yeah. So what this essentially says is permanence always lies between minus one and one. And when there is no appropriate community structure, like it can be observed or you can compute, like in grid networks, then permanence will come out to zero. And yeah, so it's like really not that hard to do. Yeah. And yeah, so here are some examples of permanence. So like this ring of cliques, which we discussed, that modularity does not handle these kinds of cases. But actually, if you calculate the permanence for this ring of cliques network, then it comes out to be almost one. So you can compute this yourself, and it will come out to be almost one. And so, like this community structure will be identified if you're trying to maximize permanence. And maybe that's a good sign for us. We want this to be detected. And yeah, and if there are wrong vertex to community assignment, then permanence almost tends to minus one. So this shows maybe like permanence is also a good metric for us. And now if we have a good metric, then what do we want? Then maybe we'll want algorithms which try to maximize this metric. So essentially we are trying to find algorithms uh, which find some community structure which maximizes the permanence metric. And what we are now doing, what we are stating is that maybe like the higher the value of this metric, the higher is the, or maybe the better is the quality of our community structure. So yeah. So again, like permanence maximization is again very similar to modularity maximization. So in modularity maximization, we did a kind of a local search, and then like Lowen's method did something more, but it was just an extension of local search only. So in permanence maximization also, what we are doing is kind of a local search, which maximizes the permanence in the network. And again, like as we said that it's basically is the similar as greedy approach, and on a high level, it is like using things like lower method. So there are two basic stages of the algorithm. First is like permanence maximization, where you just merge small communities greedily, uh, similar to like how you did, like you look at a vertex V and look at some of its neighbor and see whether merging that neighbor to V increases the permanence or not. And you keep doing this till permanence cannot be increased further. Yeah. And then what you do is when you have like you obtain some kind of a community structure after this localized max local like after this local search, then maybe you try to like merge all of these nodes together and you obtain a good community structure. And then again, like on that super graph which you obtain, like similar as Lowen's method, then on the super network, you again run this kind of a local search and obtain even a super network maybe. And note that there are, even though there are two basic stages, like it's not like similar to Lowen's method, it's not a two-step algorithm. So what can happen is, so first you do permanence maximization, then you do node aggregation, and after node aggregation, maybe you can still do some more permanence maximization. And so you do this step again, and then you do this step again, till like you obtain a graph where none of these steps can be like none of these things can happen in the graph, and in that community structure, and that community structure will be around. So yeah, so it's essentially just a local search again. Like we are not guaranteeing that it will give us the optimum value. Like it won't give us the global maximum, but it will somewhat give us the local maximum. And like for all practical purposes, probably we are just fine with it. And again, like I said previously, that any measure like which just computes a single value for like for a whole community structure, it just assigns a single value. One problem which can arise is like the mapping may not be 1-to-1, and yeah, there can be some issues. Like so, there are some limitations and some things which can be handled in permanent maximization. So it reduces the problem of resolution limit and degeneracy of the solution. So note that it reduces the problem. Like somehow, like you can show that this the one-to-one mapping obtained in this permanent maximization. Like although the mapping is still not 1-to-1, but still like degeneracy reduces. The problem of degeneracy still remains in permanent maximization. Note that this problem really cannot go away if you're trying to like approximate the whole community structure with just a single metric value. Then this issue cannot go away ever. But it does not mean that like we cannot reduce the issue. So usually it's observed in this permanent maximization things that there are less number of solutions corresponding to the same value. So the solutions are less degenerate, although they are still, but they are less degenerate. And similarly, the problem of resolution limit also kind of reduces. Again, like this does not go away because, as I said, like we can't really have an algorithm which finds everything perfectly, but yeah, it somewhat reduces the problem. Like from what like like it's a better metric than modularity because in some cases because like it reduces the resolution limit and the degeneracy. These problems still exist, but not to that extent which was there in modularity. And the other thing is, as I said previously, that uh, modularity was a global metric, whereas permanence is more of a local metric. Like although you can have a localized modularity metric also, which like is discussed in the lectures, but we leave it for now. Uh, but uh, it's easier to compute the permanence value in dynamic settings because as soon as a new vertex arrives, if you have to change the value of modularity, then you have to change look at the whole network again and the community structure of the whole network again. But in permanence, what you just need to do is maybe just look at the updated permanence values for the vertices which are updated. Like so when you have a new vertex v which enters, then you don't need to recompute the permanence from scratch. You just need to recompute the permanence for those vertices uh, for which the community assignment has changed, and this is really nice for us. Yeah. uh, but still one issue uh, which happens is like okay, like so far what we have been discussing are like algorithms which work in better in cases which where the communities are disjoint. But if the communities are overlapping, if the communities overlap with each other, the permanence maximization or modularity maximization, all of these things uh, like have a lot of issues. Like these algorithms kind of really don't work when you're trying to find overlapping community structure. These only work good when you're trying to find disjoint community structure. So these algorithms were designed keeping in mind that you have disjoint community structure. So yeah. And another thing like which is observed like through experiments in real world networks, it's observed that permanent maximization tends to produce smaller community sizes. So as you can see, there is no like one single best metric. Like usually what measure metric do you choose or what measure or how do you do algorithm? Since all of these are just heuristics, so it's up to your real world use case scenario. Like suppose maybe it can happen that maybe in some kind of social network, maybe in publications like research paper publication social network, maybe this permanence is a better metric, whereas maybe let's say in a network of Facebook, modularity is a better metric, and so on. So there are n kinds of metrics, and there can be n kinds of measures where these like each of these is the best metric for one thing or the other. Yeah. So yeah. So then, but yeah, but mostly this was the summary for like disjoint community detection. And now maybe let's just move on to like overlapping community detection. So what if the community vertices can overlap with each other? So really, the algorithm which we handle till now are really not good for those kind of scenarios. And so here we need some new ideas on how to do overlapping community detections. So yeah, so so one of these methods is this clique percolation, which was proposed by Pala et al. In 2005. And the basic idea for this method is like quite simple. It just iteratively finds and merges cliques of size k to form k plus one cliques. So what it does is okay, like initially let's just say we find cliques of size 3 in the graph. So like we just find all the triangles present in the graph and list out all the triangles. And now what we'll want to do is we'll want to move on from these like size 3 clicks to let's say size 4 clicks, like finding out size 4 clicks in the network. And how do we do this? Maybe we just try to find maybe 2 clicks which just differ in one vertex of the network. So like suppose there is this click 1, 2, 3, and there is this three size click like 2, 5, 6. Okay, maybe this is not a good example, but let's just check like this 1, 2, 3, and then this 1, 3, 4. So there are these two clicks, and both are of size 3. And now what we'll do is uh, so these two clicks we know, and then maybe we'll just try to merge these two clicks into uh, a single bigger click, which is like 1, 2, 3, 4. So it won't exactly be a click, but you'll say that it's a super node. So this becomes a super node. Similarly, here also like this 5, 7, 8 is a three size click, and then similarly the 6, 7, 8 is of three size click. So both of these differ in just one vertex. So when you take like union of these, this will contain four vertices. And iteratively, you can refine this graph, keep refining this graph till uh, you cannot merge anymore. And the final structure which arises is what you will call your final overlapping community structure. And like you can easily see that the communities formed here can be easily overlapping because a vertex can participate in multiple cliques. So it's quite obvious. Yeah. So this is one method which is click percolation for community detection. There are uh, like, so it has some issues like obviously like as you may have figured like anything which we are doing with clicks like previously also had some issues, and similarly this method also had some issues. So there is no fixed value of k. So what do we mean by k? So there is really no fixed value of the at what point do we stop in the algorithm, or what's the size of the maximum click which we want, like at which we want to stop the algorithm, or we don't want to grow the clicks any further. So we really don't know if there is no fixed value. This can change. Like you can keep k equal to 3, k equal to 4, anything works. And it is really not easy to find what's the best value of this k for a given time. Yeah. And second problem is okay, like finding a click in a network is computationally very expensive. So as you may have guessed from the previous week's assignment, so like there was a problem similar to this. Uh, like for a click of size k, you need at least like for finding a click of size k, you need somewhat like n raised to the power k amount of computation time. And if this k gets larger, like let's say k is 100, like in a network with billions of nodes, 100 size click is really not that big of a deal. And like if you're finding this 100 size click, then n raised to the power k is n raised to the power 100, which really is like impossible for us to do. So yeah, so this is like really computationally expensive. And yeah, this method is more like pattern matching applied to the network. So yeah, it's not a limitation, but more like a property or observation. But yeah, these two are like limitations for this click calculation. Then again, we propose another method. So again, a lot of this course and a lot of these modules are just based on maybe having some kind of problem, like we have the problem of community detection, and then a lot of people just proposing a lot of heuristics for these problems. And some heuristics can work better in some settings, some heuristics work better in some don't. And like it's us up to us to gauge like what kind of heuristic may work best in what situation. So yeah. So in link partition, in this heuristic, what happens is so in this link party, so this is a like pretty nice idea. I like this a lot. Like in this link partition, what happens is we really don't try to partition the vertex set say, of the graph. Since we are detecting overlapping communities, maybe like a good idea is to use actually the edges in the networks to detect communities. So what the high level idea? The high level idea is that you create a line network. And what's like a line network? So basically you create a line graph, which is just saying that, okay, maybe from a given graph G, like you create a graph where you consider all of the edges as well. So this has been covered in the lecture, and I'll just give an example also. But let me just, so the high level idea here is, okay, like instead of partitioning the vertices of the graph, let's try to partition the edges. So I like this idea a lot personally. And how do we do this? So maybe let's just create a new graph from the given graph where the edges are actually the vertices of the graph. And the vertices of the original graph will correspond to the edges of this new graph. And then maybe we can do some disjoint community detection algorithm in this new graph, and that will be good enough for us. Or like there are some other methods which we can do, but the high level idea is, okay, maybe just from the original graph, making this line graph and finding disjoint communities inside this line graph. And it can actually be shown that, like, yeah, like it can be easily seen that a disjoint set of communities in the line graph will correspond to like overlapping communities in the original graph. So let's just maybe give an example of like how to construct a line graph. I won't go into the algorithms, but yeah, suppose this was the original graph which was given to us. So there were six vertices, 1, 2, 3, 4, 5, 6, and there were like 1, 2, 3, 4, 5, 6, 7, 8 edges. So now what we do is we create a node for every edge in the network. So this 1, 2 edge gets a node. This gets a node. So all these edges, so there are 1, 2, 3, 4, 5, 6, 7, 8 nodes corresponding to 8 different edges of the original graph. And then what you do is, so you add an edge between any two vertices in this line graph if there is at least one common vertex between these two edges. So like there's an, so between edges 1, 2, and 2, 4, there is this vertex 2 common. So this 1, 2, and 2, 4, there is this vertex 2 common. So you add an edge between these two. Similarly, you add an edge between these two, and so on. Okay. And then maybe then what you can do is maybe you can run a disjoint community detection algorithm of this. So take any of your favorite disjoint community detection algorithm, and when you apply it to this, then and if you convert back the that disjoint community detection to like original network, what you will actually see is you have obtained an overlapping community, and which is also good in like, and which is of like probably a which is probably a good overlapping community in some sense. So yeah. Okay, so here's an interesting question for you guys. Uh, okay, how do I put this question? So maybe let me just yeah. So so maybe you should try it yourself. It's a really cool question. Uh, the number of edges in line graph of G. So suppose the initial graph is G, and then you're trying to take the line graph. So what will be the number of edges in the line graph? So, so this is actually equal to, okay, maybe I should insert one. So it's actually equal to summation over V and V. Um, So what am I trying to say here? That so this is like, as you may know, that this is just degree of e choose 2, which is the degree of e times degree of e minus 1 by 2. So this notation just denotes the n choose 2 notation. So we know that number of vertices in the line graph of G will just be equal to the number of edges in the original graph, because all of these edges are making the nodes in the new graph. But what will be the number of edges in the new graph? So the number of edges will actually be given by this expression. You can try this out yourself, but this is like not too hard of an argument. Like it can be done like using basic high school counting methods. And the essential idea is so suppose for any given vertex, let's say this is the vertex V which we are considering. So corresponding to this vertex V, how many edges will be present in the line graph? So for this, how many edges will be present? You just take all the edges which are touching this vertex V. So there are these three edges touching this vertex 2, and all these three edges will have some nodes. Like all these edges will have a unique node corresponding to each of them. There will be three nodes corresponding to these edges, and then all these edges will be like all these all of these no like edges will actually have a edge between them in the dual graph because of this vertex 2. So then if the degree of this vertex 2 is 3, then three edges will be added in the line graph due to this vertex 2. So that's why like each vertex contributes like if a degree is like x, let's say, then that vertex will contribute x choose two edges to the line graph, because you can pick really any two of the outgoing degree edges and just make an edge between them in the line graph. So for example, here let's just see like how many edges have like this vertex 2 as like a neighbor. So let's say so this 2 contributes to this edge. So this, yeah. Okay, so maybe let's just verify this formula. Uh, yeah. Okay. So maybe let's just okay, instead of looking at this like this, maybe let's just verify the formula for this graph. So how many edges will be how many edges are present in this dual graph? So the dual graph's number of edges present are like 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, something like this. Uh, okay, so there it's a bit confusing to find the number of edges here, but okay, so let's just count the degrees of individual. Let's see. So 3 plus 2, 5, 1, 2, 3, 4, 5, 10, 16, 1, 2, 3, 4, 5, 21, then 26, 31, and 33, 30. Yeah, it's like 34. So 34 divided 2. So there are approximately like 17 edges here. Okay, so there are 16 edges per paragraph. Okay, maybe I may have miscounted. Okay, let's just see like whatever is the number 16 or 17, and let's just count the formula here. Like what does this formula say? So how many edges are there? So there are two out. There are three. The degree of this vertex 2 is 3, or maybe let's just start with vertex 1. So for vertex 1, there are two edges. So degree. So 2 choose 2 is 1. So this contributes a value of 1. Then this vertex 2 contributes 3 choose 2, which is 3. So 1 plus 3 is 4. Then this 2 choose 2 is 1. So yeah, 4 plus 1 5. Then this is 5 choose 2, which is 10. So 5 plus 10 is 15. Then 2 choose 2 is 16, then 2 choose 2 is 17. So yeah, so according to the formula, the number of edges should actually be 17. So they should actually be come out to like 17 Karpagam, not 16. So probably my counting was correct. So you may have missed some edge, like I think this graph is a bit of a mess, and yeah, that's why there can be a bit of confusion. So yeah, but yeah, so it is 17. So yeah, Karpagam. So but the bottom line is like I just wanted you to verify this formula. Like, so I hope this formula makes sense. Like So you don't have to really count the edges in the line graph. You can just compute the number of edges using the simple expression. So does this make sense, Fagan? Okay, it makes sense. Nice. So, yeah. So maybe let's just move on to the next idea. Okay, so yeah, these kinds of methods are more algorithm. So the methods discussed till now are more algorithm oriented, and but like these days, or maybe like from a long time, like some machine learning models, like things involving machine learning, people have been trying to use machine learning models also for these kinds of tasks. And like one such idea, like maybe for overlapping community detection, is this big plan, which is actually a generative model. So it kind of uses the concepts which are used in machine learning models also. And so what it tries to do is it kind of tries to parameterize the network in some kinds of parameters and associates a loss function to the network. And then it tries to like minimize the loss using some kind of like using some kind of a loss function and gradient descent algorithm. So the high level idea is maybe like so what we do is so note that there can be so what happens is there are communities in a network and then like every vertex can lie in some of these communities, like since it's overlapping community detection, like a vertex can lie in multiple communities. And so like let's say like suppose someone gives you the what are the number of communities present in the final model, like suppose number of communities is given to you, so let's say there are like two communities, and then what you have is maybe an association parameter of every node to each of these communities, like and this association parameter kind of denotes the probability with which this vertex will lie in this community. So like the like so there will be an associated parameter with this edge, which will help us compute the probability with which this first node lies in the community or not. And similarly, like and all of these things will be independent. So like so probability of edges. So this is like yeah. So this is the high level idea here that this kind of a thing will happen. And then what we'll try to say is that okay, like if graphs lie in maybe like similar communities, then they have higher probability of an if vertices lie in similar communities, and they have higher probability of having an edge between them. So the core high level idea involved here is okay, maybe you assign some probabilities to the model and all, but at the bottom line is if two vertices lie in the same community, they have higher probability of having an edge between them, whereas two vertices lying in different communities have lower probability. And so like so this AGM model, affiliated graphical model, is just like denoting this VC and PC, where V is the set of nodes, C is the set of so this is not sent, this is set. So C is the set of communities which is given to us, and M is the association parameter between nodes and communities, and PC is the overall probability of community C. And then overall probability of edges between a pair of nodes X and Y. So what's the probability with which there will be a node present between X and Y? So this will just be like so what will be the value of this probability? It will be just so note that two nodes X and Y can be simultaneously part of multiple communities. And maybe this example discuss in the lecture also that okay, so if two people are have are like are present in more communities, like then there is higher chance that they will be friends. So there will be an edge between them. There's a higher chance that there will be an edge between two nodes if they are lying in uh, multiple communities. And so like the probability with which there exists an edge between the pair of nodes X comma Y is just like 1 minus the probability that there does not exist an edge between X and Y with respect to any of the communities. So you take the product of all the communities, the value of 1 minus PC. The PC is the parameter for like with which there can exist an edge between X and Y with respect to community C. So this will be the expression for an edge X comma Y being present, and and then like there will be an expression for an edge X comma Y not being present. Okay. And then you take the actual instance which is given to you, and try to find out like the parameters associated such that so what you try to do is so you try to like maximize the likelihood, like maximize this probability of this occurring. Like in the original graph, if there is an edge between x and y, then you want to maximize the probability with which this thing happens. And so you will want to maximize this expression. But you will have to do this over all the edges simultaneously. And so you will be doing a maximization, which is like doing a log likelihood maximization or something like this. So yeah. Like so from AGM, like how do we move to BigLam? The core idea remains the same, but the thing is now like for each community, like you have like a strength parameter associated. You just don't have a direct like you just don't have direct edges, but you have something like a strength parameter, like how close is this member X to the community A. So there are some parameters associated for all the nodes and all the communities, and each community links nodes independently. So if two nodes are present in the community A, let's say X and Y, then with what probability will an edge be present between X and Y? It will just be like this function. Like so this so in the general model, like we said that so in this model we said that the value should be something like PC, and we actually like in this BigLab model, this PC is set to something like this exponential function. So 1 minus exp of minus of f of x a times f of y. So this is something like which is not formula derived, but which is something which we take as granted in the model. So this is something which we take inside the model, that this will be the probability with which we will be doing things. And then overall probability of an edge between two nodes will just be like the expression will be like 1 minus of like, so the expression for an edge between two nodes will just be this probability. And note that this PC is again 1 minus e to the minus fx times fy. So this whole thing will become like something like e to the fx times fy. And then taking the product of all of these, so like the multiplications will become addition is the exponent. So the final result will become something like overall probability of an edge between two nodes will be like 1 minus exp of minus fx times fy transpose. And then yeah, and this is like not too hard to see, like yeah. So probability, like so this is like the derivation, which is like quite easy to see. And maybe we can have an like example here, like where this kind of thing happens. Uh, so what happens is, okay, now what you do is, hmm, yeah. So what, maybe we'll come to the example later, but here what we then do is, okay, so now we are given a probability distribution. And now what we want to do is, and also we are given an instance on which we want to find the community structure. Then what we actually want to verify is whether this instance can actually be achieved with good probability from the given probability distribution. And that's what you call the likelihood of that instance. And so what you would like, what you would want is that the instance which is given to us, the network instance which is given to us, should have the maximum possible likelihood. And that's why like this f star, like this is what you call like maximum likelihood estimation. Like this is a very, if you are familiar with machine learning, this maximum likelihood estimation is a very common technique used. And yeah, so what you are trying to do is, okay, so in what's the likelihood if I take a sample at random from my like AGM model or like BigLam model, what's the probability with which I will obtain the actual network at hand, which I actually have? So it will just be like, so for all the edges present inside my network, I will multiply all the probabilities. And for all the edges not present in the network, I'll just multiply 1 minus of the probabilities of that edge being present. And you just have to maximize this expression with respect to those association parameters, zx's and so on. And then which can just be done using a gradient descent. Since this is a maximization, so you won't be using gradient descent, but rather a gradient ascent, because you want to increase it. And yeah, so this is like trying to maximize this is equivalent to maximizing log of this. And usually like it's done in ML that you maximize the log likelihood because it's easier to deal because you don't have these exponents then. So coming back to one of the examples, maybe like because this became a bit high level. So maybe let's just quickly go through this. So let's just suppose, so there are, let's say, uh, yeah, let's just say there are like three vertices and four communities. Like, so, and we are given these kinds of FU, FV, and FW vectors. Okay, yeah, yeah. So these are like vertices, and like, so for vertex U, the community association factor with uh, community 1 is 0, with 2 is 1.2, with 3 is 0, 4 is 0.2. So that these kinds of values will be our parameters in our like final maximization problem, and we'll try to maximize these parameters. But suppose these parameters given to us, how do you do the computations? So what you're essentially doing is, like, suppose you want to find out the probability with which u comma vh will be present. Then what you just need to do is, you need to take the dot product of these values. So 0 times 0.5 will be 0, plus 1.2 times 0 will be 0, plus 0 times 0 will be 0, plus 0.2 times 0.8. So like from community 4, like this factor comes into the picture. So because of community 4, like there can probably be an edge between u and v, and this value will come out to be 0.16. And so the probability with which an edge is present between vertices u and v is just 1 minus exp of 0.16, which is 0.14. Similarly, probability with which an edge between u and w will be present will just be, you again take dot product between these two vectors, 0 times 0 plus 1.2 times 1.8. So this will come out to be 1.5 times 1.8 will come out to be 225, 216. So it will probably come out to be something like 2.16, I believe. Yeah, it should come out to 2.16. Yeah. And then you just do 1 minus e raised to the power 2.16. 1 minus e raised to the power minus 2.16, and it should evaluate to like something like this. So you can verify this also. I'll also just try it out in the calculator. So yeah, it indeed comes out to like 0.88. So yeah. Similarly, for edges VW, the dot product will be, this will be 0, this will be 0, this will be 0, this will be 0. So the dot product will just be 0. So 1 minus e raised to the power 0 will just be 0. That's why like probability that an edge between V and W will be present is 0. So I hope this makes sense. It's a bit tricky, but like if you like know the basic ML techniques like log likelihood maximization or like maximum likelihood estimation, essentially, then this is really like not that big of deal, this model. But yeah. And now like yeah, as I said, so this is just denoting what is the maths behind all of this. Just denoting the maths again. And yeah, as I said, like since you are maximizing the log likelihood, so it's not really a gradient descent, but rather a gradient ascent. Like, although you can like take the negative of that log likelihood and then just say you are trying to find a gradient descent, but like, yeah, everything is fine. Okay, then. Okay, maybe then. So there are a lot of things which we need to cover. So maybe we should not cover a lot of these things, and I should leave it to you guys since you have already seen these. Okay, so maybe let's just leave it at big clam for now. Like I have like still took screenshot of the slides for the further techniques for community detection, like label propagation, or like which can be of form asynchronous or synchronous label propagation. So these are quite easy to like understand technique. Like these are not too difficult. And then there are like as I said, like there's this notion of local modularity. So you can view these also in the lectures. These are, although these are not discussed much in detail, this local modularity measure, but it's still something like which you can look at if you are interested. And then maybe one last thing is like, yeah. So one problem which we previously discussed was the community detection, where you are given a whole graph and you want to find out the communities present in the network. But another problem can be, which is kind of an easier problem, is the community search version, where what you just want is, okay, you are suppose someone asks you a query that you're given a vertex v, what community does that vertex belong to? So suppose you are given a lot of users in the network. Uh, yeah, suppose like there's a Facebook network with billions of users. And then one thing is to maybe label all of these users in some form of communities, which will be community detection. But then what is community search? Like suppose someone comes and asks you specifically like, which community does Lakshay belong to? And that will be community search. And as you can see, if you know like community detection, like what's the community of every node, then answering the community search query is easy. But for a vertex specific vertex v, if you know the community search, you really don't know the whole, like you can't detect the whole community. So this is like so this community search is somewhat of a easier version of community detection. Like it's just a query dependent version. So all the community detection algorithms are also applicable to the community search. That's why like this community search is somewhat of an easier version of community detection. Because if you have detected communities, then you can search from them easily. But if you know like search the answer to a search query for a single vertex, then you really don't know the whole community structure of the network. That's why community search is somewhat of an easier problem, considered as an easier problem than community detection. And yeah, so similar kinds of techniques like K-core, Clay-Click, KECC, and everything, which we discuss for community detection, apply for community search also. But let's not get into that. And then there were like so till now what we discussed was uh, like some metrics on how do you actually do community detection, or like what are the possible ways in which you can do community detection. But note that this is really not enough. Like we need to, so as I said previously also, how good a community is, like how, like suppose someone outputs you a community like assignment of the network, then how good is this assignment is again a problem on its own. And we define various metrics like modularity, cut ratio, permanence, and everything. But note that we need some more global measures to compute this, like how good a community is. Because like all of these modularity, etc. So suppose, like this was discussed in the lectures also, suppose you take the evaluation metric as modularity only, then an algorithm which is like which maximizes modularity will always be the better algorithm, even if it is like a poorer metric, even if modularity is a poorer metric. So then there are things like things proposed like community like purity score. So maybe we have a question about purity score later. So maybe we can uh, discuss like these things, or maybe like you can view these like, so these things are really not too difficult. So purity score is just like, so suppose like, so suppose you have some like ground truth label. So it is similar to like in machine learning, what you have is like training data or something like that, where you actually know the labels. Like if you actually know the community labels of different nodes in a network, and suppose your algorithm outputs some predicted labels, then what's the purity score defined as like so C is the labels which are actually the actual labels, and omega is the set of labels which your algorithm provides. Okay, so Karpagam, you want me to explain what is true negative? Okay, like I'll just explain this in a minute. I'll come to it. Then purity score is nothing but 1 divided by number of vertices and summation of maximum over omega j intersection ck over j. So what this essentially means is, I think this was covered nicely in the lectures also. So what this essentially means is that uh, for every ground truth community, you take the predicted community which overlaps the most with this ground truth community, and you just take the sum of the number of overlaps over all the ground truth community, and this is what you call the purity score. So for example, in this, like suppose these circles are the detected communities, and these shaded things are the ground truth communities. So for the ground truth community, let's say the black community, uh, like uh, this black community intersects with the detected community here the most at 4 vertices. Here it does not intersect, and here it does not intersect the ground truth community. So the so it will like correspond to 4, So the sum will give like 4 for like so ground truth communities are shades and detected communities are 3 large circles. So uh, the black ground truth community will contribute a factor of 4. Similarly, this shaded community which has like a 1, 2, 3, 4, 5, 6, 7, 8. So some of these nodes, out of these nodes, like with which of the detected community does it intersect the most? So this is the community with which it intersects the most at 5 vertices. So then it will be 4 plus 5 plus like, and this thing intersects the most with this jet community 2, which is just 3. So 5 plus 4 plus 3, which is like 12. 12 divided by the total number of vertices, which is like 5 plus 5, 10 plus 6, 16. So 12 by 16 is like 3 by 4. So yeah. So this is how a purity score is evaluated. Similarly, you have something called RAND index. And what is RAND index? So RAND index is just defined as like this. All of these are like very standard things if you're familiar with machine learning, like precision, recall, and there are a lot of things, but let's not get into all of those. Like I'll not discuss the F1 score and everything because yeah, I don't think they are really. So there can be n number of metrics, and I really don't want to discuss everything. You can just read them up or listen to the lectures. But yeah, so I think RAND index is important because RAND index just says that it's just the ratio of true positives to true negatives to the total number of instances. And how do you define all of these instances? So a true positive is a pair of nodes in the same community in the predicted and ground truth community structures. So note that uh, yeah, for any pair of nodes, like so suppose RAND index is just based on maybe like suppose we are defining an index only for like disjoint community detection. So RAND index is usually used only for disjoint community detection, evaluating disjoint community detection, not for overlapping. So if you have like disjoint community detection, then for any two nodes, either those two nodes belong to the same community or they belong to different communities, right? So and there are like ground truth and your detected truth, your detected communities. So uh, so if your predicted and ground truth communities both say that two vertices are in the same community, then it's counted as a true positive, that pair. And a pair is counted as a true negative if like the ground truth is also that the two vertices lie in different communities, and you also predict that the two vertices lie in different communities. And similarly, false positive is like you say that they are in the same community, but ground truth is that they are in different community. Similarly, false negative is uh, like what false negative is essentially like you are reporting that they are uh, different communities, but it is false, but actually they are in like the same community. So does this make sense, Karpagam? So this like positive, negative terms. So the second part comes from your detected thing. So like if your detection says that the vertices are in the same community, then it will be positive. If your detection says that they are not in the same community, then it will be negative. And if your prediction is correct, then you attach a true to it. If your prediction is incorrect, then you attach a false to it. This is how these four terms are defined. If this makes sense. Like by true negative, what I mean is, okay, this true negative means that I am reporting negative. My predicted algorithm reports negative, and it is actually true. So what this means is that my predicted algorithm says that it's negative, and in reality also it is negative because like my predicted algorithm is true. So yeah, okay, it makes sense. So nice, Kalpan. Yeah. And then what you just do is this random index is just true positive plus true negative divided by. So note that true like any pair can be one of these four cases only. They cannot be anything else. So this denominator is just the total number of possible pairs. Because any pair can either be true positive, true negative, false positive, or false negative. There cannot be really any other. So this is just the total number of pairs, and this true positive plus true negative is essentially saying that so true positive plus true negative is essentially saying the number of correct predictions which you are making. We don't matter whether the predictions are about like positives or negatives. but you are making the predictions correctly. So this random index is just like total number of correct predictions divided by total number of predictions in a nutshell. And then there are several other metrics, precision, recall, from which you calculate F1 score. There are entropies, mutual information. So let's not get into that. If you want, like, you can read it. Like maybe a lot of these things are not even covered in the lectures because a lot of these things are just standard machine learning stuff. So one can just look them up because these are like some definitions. Oh yeah, like you can look them up online or you can just look them up in the lectures. But now maybe let's just move on to the some of the questions. So I don't have a lot of questions for today because I think we are short of time, but let's just get with it. Yeah. So first question is, so what's the modularity for an unweighted graph, for an unweighted and undirected graph, which is a clique with n nodes? So there's an undirected clique with n nodes. So there are like n nodes and each pair of nodes is connected to each other. So what is the modularity for this, assuming there are two communities with n by 2 nodes each? So suppose your community detection algorithm uh, outputs two communities which are n by 2 nodes each. So I should write that disjoint. So the initial graph is a clique with n nodes, and your algorithm outputs two disjoint communities with n by 2 nodes each. Then what's the value of modularity for this? This kind of a so this is your output. And so how good is this community detected output? Like how good is it detected output? So this is measured using like the mod, like let's say with respect to modularity, what's the modularity score for this kind of an output? So since there's a shortage of time, maybe like Karpagam, you can try, but I'll also like solve it in parallel. So the formulation, so the idea for this is just, so this is the formula for, so this is just a plug and play formula here. So uh, so this is the formula for like modularity, and here the communities are like so first community, like there are two communities which we have, both are of size n by 2, so we'll just plug all these values inside this formula. So maybe let's just do this. Yeah, so maybe I'll just insert an equation, and maybe I'll just copy and paste this formula here so that it's easier for us to look at this one. Okay. Yeah, one should ideally be remembering this formula because it's like it will take a really long time for you to like derive it in exam. All the derivation is not so hard as we saw in the lectures, but still it's good to remember this formula. So maybe like let's just see here. So we know that what's the value of Q. So Q is just a summation over both the communities, the value of this. So let's just take this it over first community, which has n by 2 nodes, which are all connected to each other. So since it's a clique, every pair of nodes is connected to each other. So like between inside one community also, like every node will be connected to each other, right? So it will be like so for the community one, it will be like mn by e. Mn denotes the number of edges in the community n. So mn by e will just be like yeah. So numerator will be this mn, which is like number of edges in the community n. Maybe I should write it as 2, so that like I don't have the fractions. Yeah. So the numerator will be just the number of edges in the community n, which will just be equal to n choose 2, because there are n nodes in the community, and so the number of edges will be just n choose 2 edges. And the denominator will be the total number of edges inside the clique, which is like 2n nodes. So the total number of edges will be like 2n choose 2. Yeah. 2n choose 2. And then minus this kn, uh, this kn divided by 2 times e whole square. So what's the value of kn? Kn is just summation of degrees over the vertices inside that community. So Maybe I'll just put a fraction here also. So this Kn is just summation of degrees over the vertices inside the community. So note that there are n nodes inside the community, and for all of these n nodes, like uh, the degree is like something like 2n minus 1, because every node has an edge to like the other 2n minus 1 node. So this will become something like n times 2n minus 1 divided by this thing, which is 2 times the number of edges. So 2 times number of edges is 2 and choose 2. So you will just, maybe you can just write it as 2n times 2n minus 1 divided by 2. And the 2 and 2 cancel out here. So it will just be like this. And yeah, this square. Similarly, like we can simplify this also. So this 2n choose 2 can be written as maybe 2n times 2n minus 1 divided by 2. This can be written as 2n times 2n minus 1 divided by 2. But that 2 is cancelled out when you write it as n times n minus 1. So this will be the formula. But this will be with respect to one community structure. And similarly, like since there are two disjoint communities, like so first, with respect to first set, this will be this, and the second set also the value will be the same. So the final answer will be like something like this. So 2 times uh, this expression. Um, this work here. Okay. Yep. So this will be the final answer for us, for the community, like for the value of modularity if the output is two disjoint communities with n nodes each. And let's just try to see like if we can simplify this further. So this will become 2 times, like in the parentheses this will be just, so n and n cancel out, and this will become n minus 1 divided by 2 times 2n minus 1, and then there will be a minus. So this 2n minus 1, 2n minus 1 cancel out, and this n cancel out, and this just becomes a half. So this becomes half squared, which is 1 by 4. 1 by 4. So this is the answer. Fine. Maybe I'll just try this, which is like this 2 and 2 will cancel out. So this will be just n minus 1 divided by 2n minus 1 minus half. So this will be our final answer for modularity. So I hope this makes sense to everyone. Yeah. And actually you can see that this will always be less than 0. So note that this assignment will always have modularity less than 0, because this thing will always be like, you can verify it yourself that uh, this thing will come out to be negative always. So yeah, so which is less than 0. So actually, like this assignment is probably not a very good assignment for us. Like gives us negative mark. But yeah, nonetheless, let's just go on. So second problem says that which of the following are disjoint community detection algorithms? So which of the following algorithms are disjoint community detection algorithms? So we saw that Loven was used for disjoint, BigClam was for overlapping, click population was for overlapping, Infomap, I don't know, maybe just let's just remove Infomap. I think we did not discuss it. So the Lovan, BigClam, and click population, like I think maybe it's really a multiple choice also. So, Lovan is the answer. So is this option A, as discussed in the lectures. Yeah. So yeah, good job, Karpagam. Yeah, Lovan is the correct answer. Then in the third problem, in the BigClam method for overlapping community detection, do we use gradient descent or gradient ascent for maximizing the log likelihood? So I just discussed this, Karpagam. So if you're paying attention, like maybe this is a thing which you can answer. Do we use gradient descent or gradient ascent for maximizing the log likelihood? Yeah, gradient descent. So good job. Yeah, gradient descent. Gradient ascent. Again, the answer as discussed in the lectures. Yeah. Okay. Uh, yeah, maybe I think this is a bit of a numerical. Yeah, it will be a bit tough to calculate it right now since we are short on time. So if we are given this community assignment, which assignment will be preferred if permanence is considered to be a deciding metric? Okay, even though calculating the actual values might be a bit difficult here, like as you might see, like there are a lot of nodes, so calculating permanence will be difficult. But uh, can you answer this, Karpagam, even if without calculation? Like which of the following community will be preferred? Like although like it will be really like time consuming if you do this using like actual uh, like using actual calculation and calculating permanences and all. But I believe like you can do away with a lot of calculations. Like even though like uh, you don't do actual calculations, but like intuitively, like so all of these things, permanence or modularity, all of these things kind of try to like form community structures, right? Better community structures. So at the core, like this is a much better community structure than this core, than this, right? Because here these, yes, exactly. So good job, Karpagam. So option one should be the correct answer because here, like all of these nodes which are in this cycle are like these seem to be like forming a much better community because they form a cycle than like these nodes where there is really no structure between these, like being a community. So yeah, so answer should be option A. Like although I'm not calculating the permanences, but like with with high priority, I can say that the answer will come out to be permanent. Option A, even though the final answer should be based on calculating the. So usually, like if you are unsure in some scenarios, then maybe it's a good idea to check for the permanence, which of the following community assignment is better. But here, I think it's very visible to the naked eye. Like it should be better in the option based on calculating the actual. So this is again like this is a heuristic solution, which I'm saying. Like this is not the actual solution. Actual solution will have to go through the values. So this heuristic can sometimes be incorrect, but most of the time, like it will be much more efficient than calculating the whole value and will be probably give the correct answer. Values. It's easy to see that option one has better community structure and hence probably higher permanence. But yeah, then maybe let's move on to the fourth question. So what is the modularity of a network with n nodes if all the nodes of it belong to a single community? So what will be the modularity of a network with n nodes? Suppose there is a network where like there is only a single community in which all the nodes lie on. Can you just guess this? So again, the formula is based on right. So here, like all the nodes are lying in the same community. So what happens is, so the summation is over a single community, and just mn denotes the number of edges inside the community n. So this mn just becomes equal to the value, the number of edges in the graph. So this e by e, this value becomes 1, and then this kn. where this kn is just like summation of degrees. The summation of degrees is just equal to like twice the number of edges in the graph, right? So this ratio also becomes 1. So the final answer becomes 1 minus 1 squared, which actually is just equal to 0, if this makes sense. So does this make sense, Karpaga? Oh yeah, so you wrote answer 0. So good job, Karpaga. Yeah. So option A, as can be seen from the formula for modularity. So it's a like a really nice thing to see that okay, like if you're not forming any community, you think of whole network as a single community, then the modularity is kind of 0. So 0 is considered a baseline in our example. Like if you don't have any community structure, you just think of whole graph as a single graph thing, then it is 0. There is no really community structure. We yeah, I should probably have to. Okay, so good job, Karthagam. Now maybe let's move on to yeah, question 6 and 7. So this will be good practice for you, like yeah, maybe I should move this question. Yeah. So given the result of a community, so community detection, like so there are like some ground truths which are so in the problem for 6 and 7. So this is the diagram. So there are these ground truths which are these squares, circles, and these diamonds, and the detected communities are these ovals. And now like we want to find out the purities and everything. So yeah, maybe let's just move this diagram to the next page so that it's easier for us to work. So now the problem statement is find the purity of the given prediction. Okay, so let's see. So Karpagam is saying something like this. The sixth fact should be therefore. Let's just see. So if we have to find out the purity for this kind of a prediction, so what we'll say. So let's just take the ground truth class 1. Maybe let's just say. So purity here will be something like yeah. So let's just take the ground truth class 1. So ground truth 1 is, let's say, this squares. So the squares have maximum intersection of like 4 with this, 0 with this, and 0 with this. It will be max of 4, 0, 0 plus max of. So let's just take now ground truth true. So ground truth true is like ground truth 2 has like 1 intersection here, 2 intersection here, and 5 intersections here. So it will be 1, 2, 5 plus max of. Let's just take the ground truth as the circles now. So it will be 0, 3, and 1. So max of 0, 3, and 1. Yeah. And all of this are divided by the total number of nodes. So this is just a normalization factor. But how many nodes are there? So 4 plus 1, 5, 5 plus 5, 10, 10 plus 60. And this comes out to like, this is 4 plus 5, which is 9, plus 3, 12. So is this the same example as what we discussed previously? So that also had 12 by 16, which is 0.75. I should probably not give the options. This is the same. Like, okay, so 0.75. Let's just see. Maybe like the example which I gave is the same as this question. Oh yeah, I think these are same. Oh yes, like just the things are different. Just the diagram is different, but the actual like distribution is the same from that example. That's why like the example was 3 by 4 in both cases. Okay, Karpagama, second term. Okay, so how do you do the uh, so how do we do the community direction here, Karpagam? So what we do is, so we have these ground truth labels. These squares, diamonds, and circles are the ground truth labels, right? So let's just take the ground truth as square. So what we do is in the formula, what we do is we take the ground truth and we see how much does that with what community does that ground truth intersect the maximum? With which detected community? So maybe let's just look at the formula again. So these k's are the set of ground truth community labels, and omega 1 to omega j are the set of predicted community labels. So what you do is for each of the ground truth label, you fix that label k, and then you say like with which of the detected community does it intersect the most. So I think in this formula, like, okay, I think you're a bit confused by the formula used here. I think the formula used here is a bit incorrect, even though answer comes out here as 0.75 also. But I think the formula used here was like a mistake in the lecture. It should really not be this, but the one which I actually use. Because like what you have to do is you have to consider all of the ground truth at once. Like, so first you consider the ground truth, which is this black ground truth, and you have to see the maximum number of intersections of this black with the detected communities. So black intersects with 4 in the first thing, 0 in the second, and third is the second. So this term should really be max of 4, 0, 0. Then the second term will be like for these, let's say, shaded regions. So that for this shaded region, it should be like it intersects once here, twice here, 5 times here. So it should be max of 1, 2, 5. Like it should not be like 0, 5, 1. It should be 1, 2, 5. And then for the third thing, which are just these circles, it should be like max of 0, like these have 3 circles, so 3, 1. So max of 0, 3, 1. So yeah, like even the answer from this formula and from what I use comes out the same, but actually like yeah, there was a mistake in the lecture. Sorry, I forgot to mention this while going through this part. But yeah, the formula used in the lectures had a mistake. Like because this is the correct formula for purity, and then maybe these steps, like even though they lead to the correct answer, but yeah, this is probably like not the way to go about it. It's like, what I have written is the correct way. If there are any changes, probably like it might be the case that maybe I'm misinterpreting this, but I'll just check it once again. And if there are any changes, like anyways, I'll be posting these to the Google Drive folder, and so I'll make the the desired changes. So if there are any like issues, then I'll inform you guys. So don't worry. But I think like this is the correct way. Like the one used in the lectures is really not the correct way. But still, let's just okay. So maybe like this. So let's just do this. The last thing. So find the RAND index of these predictions. So maybe let's just find out. So for finding the RAND index, we need to find out first the true positives. Okay. So yeah, so it's a bit of a book. So how many pairs are there? So there are so how many pairs are there? So let's just look at the total sum, like true positive plus false positive plus true negative plus false negative. What will be this equal to? So there are 1, 2, 3, 4, 5. So there are 16 vertices. So there will be 16 choose two pairs, right? So it should be 16 times 16 minus 1 divided by 2, which is like 15 times 8, which is 15 times 8, which is 15 times 8 is equal to 120. Yeah. And then we have to find out the true positive pairs. So true positive pairs will be the ones, the pairs which are actually in the same community. So they are positive means they are like our detected community detects them in the same our detection algorithm detects them in the same community, and they're actually in that ground truth also says that they're in the same community. That's why it's a true positive. So maybe let's just look at the pairs. So let's just take the community one. So in community one, maybe all these pairs like all these vertices are present in the community one are like uh, detected as positive by our algorithm. But out of these, how many are indeed positive are these 4 vertices, right? So with respect to this community one, the contribution to true positive will be 4 times 4 minus 1 divided by 2. And with respect to community two, so here in community two, what we have is these three vertices are actually like corresponding to true positives. So they will correspond to 3 choose 2, which is 3 times 3 minus 1 by 2. And then we'll have like, yeah, so, yes, so it will be 3 choose 2. Similarly, here it will be 2 choose 2. So here it will be like 2 times 2 minus 1 divided by 2. So corresponding to these two. And here then we'll have like, okay, so this is not a pair, so this vertex won't contribute, but these 5 will contribute. So we'll have something like 5 times 5 minus 1 by 2, right? So it's like, so this comes out to be 4 into 3 by 6, 4. So this will be just 6 plus 3 plus 1 plus 5 times 4, 5 times 2, so plus 10. So it will be 6 plus 9 plus 1, 10 plus 10, 20, which is 20. And then, okay, so then we we want to calculate the false positives, we want to calculate the false negatives. Okay. Then like true positives are easy to find. Similarly, like uh, which pairs are, let's say, false positive. So false positive will be the ones which are detected positive by our algorithm, but they don't actually uh, are actually not part of the same truth. So here, like, okay, so let's take the community one. Here, all of these are detected in this by our algorithm to be in the same community. But note that these uh, diamonds and squares are actually like for these diamond and squares, our prediction is actually false. So this diamond and square pairing will correspond to an incorrect solution for us. So the contribution to false positive from this part will be 4 times 1. So this will be 4 times 1. And from the community 2, the output will be, so there are these 3 circles and these 2 diamonds. So then 3 times, like, so the number of pairs for which the prediction is incorrect. So our prediction is positive, but it is incorrect, is these pairs like 3 times 2. So it will be 3 times 2. And similarly, yeah, and similarly for these, like, similarly for this, like, the number of pairs for which our prediction was incorrect was like 5 times 1. So 5 times 1. So number of false positives will come out to be 4 plus 6, which is 10 plus 5, 15. So does this make sense, Prakash? Like what I'm doing till now? Similarly, if we have to report, okay, it makes sense. That's nice. Similarly, if we have to report, let's say, uh, true negatives. So what are true negatives here? So true negatives are just like what our algorithm reports as negative, and it is actually negative. So our algorithm reports that, so our algorithm reports negative for all the pairs which are like not in the same community. So let's say the first vertex speaks this from community 1, and the another vertex which speaks from like community 2. Then for this community 1 comma 2 pair, what will be the false negatives? The like the true negatives. So the true negatives will be the pair of vertices for which it's indeed disjoint. The prediction is indeed disjoint. So as you can see, like this, uh, all these squares are indeed like different from all these shapes here. So it will be like, so these are 4 squares and there are these 5. There are these 5 vertices. So the contribution will be 4 times 5 plus note that this thing, this yeah, and that like note that like if this vertex is there, then this diamond is kind of distinct from these 3 things, these 3 circles. So then it will be like 3, 4 times 5 plus 3. Okay, maybe like true negatives are a bit harder to find. Let's just find out false negatives and then we'll just subtract from the total to find true negatives. So to find false negatives, what we can do is, so our output is negative. So like we have to consider like different community pairs. So between community pair 1 and 2, let's say like what's the like how much is our prediction false? So between these two pairs, our what we detect is kind of like that our prediction is like negative, but it is actually like our prediction is false. So actually they should belong to the same community. So how many pairs between these are there, these two things that actually are part of the same community? But so like one vertex from here and like one vertex from here, such that they are part of the same community. So it's like these pairs. So this paired with these. So it will be like 1 times 2. Yeah. And yeah, for everything else, like our prediction is kind of good enough. Okay. So okay, so let's just look at Karpagam, this false negatives case again. Like okay, let's just start from scratch for this false negative. So what does false negative mean? False negative means that our algorithm predicts it to be negative, but what our algorithm is predicting is actually false. So in the ground truth, the pairs are in the same community, but our algorithm says that they are in the different community. Like prediction says that they are in different community, but ground truth says that they are in the same community. So the suppose the prediction says that they are in communities 1 and 2. So these are different communities with respect to predictions, but actually they should be like in the ground truth, they should be the pair should be in the same community in the ground truth. So one vertex from community 1 and one vertex from community 2, such that they are in the same community in the ground truth. So that case will be when like these diamond shapes are actually like in the same community in the ground truth. So if one vertex is chosen as this and the second vertex is chosen as this, or if one vertex chosen this and the second vertex chosen this, then these will contribute to like false positive, false negatives. Like for so what we are essentially saying is like the output is negative for detected community 1 and 2. Our output is negative, predicted output. But the ground truth is actually that they are in the same community. So what are the cases? So these are the cases when they are in the same community. And similarly, when you say communities 2 and 3, then when does your prediction fail? When when you consider these circles, so 3 are in here and 1 is in here. So in these pairs, the prediction fails. So it's like 3 times 1 plus you consider these diagonals. So 2 times 5. And so this is like for when we are considering detected community 2 and 3. Similarly, there will be a case where detected community 1 and 3 are considered. So between 1 and 3, the only predictions which can go incorrect are like when the ground truth is this diamond and like corresponding with any of these 5 diamonds. So it will be like 1 times 5. So this will be like 2 plus 3, 5 plus 10, 15 plus 5, 20. 2 plus 3, 5, 5 plus 10, 15. Yeah, 20. So then like what's just true negative equal to, so maybe I'll just put this true negative at the end. So true negative by itself is a bit harder to find. So what we'll do is just like, we know the total sum. So we'll just subtract from 120 all of these values. So it's just 120 minus 20 plus 15 plus 20. It will be like 40, 55. So it will be just like 65. So this will be the value of true negative. So does this make a bit of sense, Karpaga? Now, like how we calculated this, the number of false negative pairs. Like we just said that since they are false negatives, so they should lie Okay, it makes sense now. That's nice. So these are the different values obtained, and now like what's the value of rand index? So rand index is just true positive plus true negative. So true positive plus true negative is just 20 plus 65, and then all of this divided by total number of instances, which is just 120. So this comes out to be like 85 by 120, which is equal to like 0.7 points, 0.7 approximately. So yeah, this is our final answer. So yeah. Okay, so this is it what I had for the day today. So Karpagam, you're saying that you have some doubt from previous assignment, so maybe we can go through it in like maybe like, like since we are already like way above time, maybe we can do it in like a couple of minutes. So after that, I can try to answer it like fast. So Karpagam, are you there? No, I don't see you typing anything. So would you like? Can you send me the doubt what you had? Like, can you send me the doubt if you are there? So okay, so you had doubts in understanding what are K clans, K clubs, and K plexes. Oh, so one thing which I'll like uh, so one thing which I can like tell you is like maybe I think I covered like all of these like K clans, K clubs, as well as K plexes in the last lecture. Like I explained, like you can like so you probably have the YouTube lectures link, right? So you can just view the video for the previous session, and I think like I spent a lot of time on these. Oh, really? The audio was not clear. Okay. Uh, so did you try to like understand from the like lecture videos? So K clans, K clubs. Okay, maybe we can just go over them quickly. So yeah. So let's just see what were K clans. So I hope like K clicks were clear. Okay, okay. So sorry for that, Karpagam. Like, so no one was there to tell me that audio is clear or not. So I think I missed up a bit, but yeah, maybe like we can try it now. So let's just see the K clicks. So K clicks we know are like what are K clicks? So K clicks are like a maximal subset of vertices such that for any two nodes, shortest distance between them is less than or equal to K. Right. So we define a K click as the set of vertices such that the shortest distance between any pair of vertices is less than equal to K. Right. And but like one issue in defining K clicks like this is okay. Like suppose consider these vertices 3 and 5. So the shortest distance between 3 and 5 is actually 2, but the shortest path taken is through this vertex 4. So like what happens in K clicks is that sometimes even though the shortest path is less than equal to K, but that shortest path is through some vertex which is outside that click, which is something which we don't really want. Yeah, like I'm just trying to. Okay, is my screen not visible? Oh yeah, so sorry. Like I'll just share this again. Yeah, yeah. I hope it's visible now, Karpagam. Like I hope it's visible now. Like okay, yes, it's okay. So for K clicks, what I was saying was that consider this set of vertices like these are k-clicks in the sense that any pair of vertices has distance less than equal to 2. So I'm just sharing, revising k-clicks because like you can build on from intuition of k-clicks about what are k-clans and k-clubs and all. So that's why I'm just trying to do it from the start. So note that here these are 2 clicks because like between any pair of vertices in this set, the distance is less than equal to 2. But consider the vertices 3 and 5 here. So for these vertices 3 and 5, actually even though the shortest distance is 2, it goes through this vertex 4. And note that this vertex 4 does not lie in our set, which we defined as the k-click. So like ideally what you would want is like all the vertices to go through like the set which you define for the shortest path. Like, because like otherwise it's a bit of an issue for us. So like, so that's why like we need some more defined definitions moving on from k-clicks. Like, so even though this is a 2-click, but like the shortest distance, like the shortest path between vertices 3 and 5 will actually involve a vertex which is not inside the k-click. And yeah, this is an issue for us. And so we try to fix this issue by coming up with a new definition, which is k-clan. And where like we just try to relax this kind of statement, and we just say that in a k-clan, and we just say that in a k-clan, like the thing which we are saying is okay, the shortest distance between any pair of vertices is less than equal to k in the subgraph induced by those sets. So like so note that even though like for example here in this set of vertices, let's just take maybe what's a good example here. Okay, maybe like just this example here. So in this example, like it's this set 1, 2, 3, 5, and 6 is not is a 2-click because between any pair of vertices, shortest distance is less than equal to 2, but it's not a 2-clan. And why is this the case? Because between this pair, the vertices 3 and 5, the shortest distance between 3 and 5 is 2, but this shortest distance 2 is like from a vertex outside the set. So from what the shortest between 3 and 5 from inside the set, like the shortest distance is 3. So actually, this set, this 1, 2, 3, 5, 6 set, even though it's a 2-click, but it's a 3-clan. Because from this set of vertices only, the shortest distance that you can form from 3 to 5 is through this path, which is of length 3. So this set is a 2-click, but a 3-clan, if this makes sense. And then there is just another definition, which is like k-club. So the k-club is essentially just a k-clan minus the maximality condition. So maximality means that like no further vertex, we should be able to include no further vertex in the current existing set. And we just relax this definition to form a k-clan, to form a k-club. And why do we relax this definition? Usually it's done because like finding maximal set can be sometimes computationally expensive. So we just try to relax this and define k-clubs because now we can find smaller size sets and define those as k-clubs. Whereas we really could not do this for k-clans because we require this maximality condition. Yeah, but nonetheless, like all these like are computationally expensive to evaluate. But yeah. Okay, so does this clear your doubt to some extent, Karpaga? Like maybe if there are further doubts, like you can try it, like to maybe watch the lectures again, or like what I just explained, you can try to like just go through what I just explained again. Okay, so what does maximality condition mean? So maximality condition actually means that like you should not be able to include any further element in the set. Like so for example, uh, let's just consider this set of vertices, like this set of vertices. So what do we mean by maximum? That like right now, what this set of vertices, let's say, is a like 1, 2, 3, 4, 5. So between any pair of vertices, the shortest distance is 2. So it's a 2-clan. But another requirement is that we should not be able to include any other vertex into this set such that it still remains a 2-clan. Like into this subset, if you include any other vertex of the graph, and if it still remains and if still like the shortest distance between any pair of vertices is less than equal to 2, even after including some further vertices, then you don't call this a two-plan. Like, so maximality condition essentially, like intuitively, what maximality condition says is that like the set should be like of maximum possible vertices as possible. Like you should not be able to include any further vertex into this set, which satisfies still the criteria that the shortest distance is less than equal to k. Does this make sense, Karpagam? Like what do I mean by maxim? Like in general, you have this notion of maximal solutions, right? Like maximum solutions are solutions which cannot be improved further. Similarly, their maximal set is a set in which you cannot include further elements. So that's still the property ring. Okay, then it's clear to you. So that's nice. Okay, so I guess this was all I had for today. I think we over time, and I think like so if there are any further doubts, maybe I can take them up in the next session. So for now, I guess yeah. Once again, so maybe thanks for joining Karpagam today, and to everyone who's watching on YouTube for watching today. So maybe like I hope to see a few more people in person from next time onwards, like Karpagam. So yeah, but yeah, till then, like maybe yeah. Goodbye, guys. See you next time, next week, same timings, Monday 6 to 8 p.m. So goodbye, Karpagam. Thanks for joining.